The inner workings of your digital world. The modern computer, despite its sleek exterior and user-friendly interfaces, is a complex orchestration of hardware components working in concert. At its core lies the Central Processing Unit, CPU, often referred to as the brain of the computer. This silicon chip executes instructions from software programs, performing calculations, logical operations, and controlling all other parts. The CPU's performance is heavily influenced by factors like clock speed, measured in gigahertz, and the number of cores. More cores allow for parallel processing, handling multiple tasks simultaneously. Crucially, the CPU doesn't store information long-term. It relies on random access memory, RAM, for that purpose. RAM is volatile memory, meaning data is lost when power is removed. Think of it as short-term working space for the CPU. When you open an application or load a file, it's copied from storage into RAM for quick access. The more RAM you have, generally the smoother your computer will run, especially with demanding software like video editing suites or complex games. However, this data needs to be persistently saved, which is where storage devices come in. These include traditional hard disk drives, HDDs, utilizing magnetic platters, and faster solid-state drives, SSDs, employing flash memory for significantly quicker read/write speeds. SSDs are now the preferred choice for operating system installations due to their performance benefits. Beyond these core components, the motherboard acts as the central communication hub, connecting all other parts together via various buses and interfaces. It provides power distribution and allows data transfer between the CPU, RAM, storage, and peripherals. Connected to the motherboard is the Graphics Processing Unit, GPU, dedicated to rendering images, videos, and animations. While integrated graphics are sufficient for basic tasks, a discrete GPU with its own dedicated memory, VRAM, is essential for gaming, video editing, and other graphically intensive applications. Input devices like the keyboard and mouse allow you to interact with the computer, sending signals that are processed by the input-output I/O controller on the motherboard. These signals are converted into digital data the CPU can understand. Output devices, such as monitors and printers, receive data from the CPU and translate it back into a human-readable format. The entire system is powered by the Power Supply Unit, PSU, which converts AC power from the wall outlet to DC power usable by the computer's components. So, how does all this work together? When you launch an application, the operating system loads instructions and necessary data from storage into RAM. The CPU fetches these instructions from RAM, decodes them, and executes them. If the application requires graphical output, the CPU sends commands to the GPU, which renders the images and displays them on your monitor. Throughout this process, data is constantly being transferred between the CPU, RAM, storage, and peripherals via the motherboard's buses. This cycle of fetching, decoding, executing, and storing forms the basis of computer operation, known as the fetch-decode-execute cycle. Finally, understanding the concept of bandwidth is crucial. Bandwidth refers to the amount of data that can be transferred per unit of time. Higher bandwidth for RAM, storage interfaces like SATA or NVMe, and buses on the motherboard translates to faster overall system performance. The interplay between all these components, CPU speed, RAM capacity, storage type, GPU power, and bandwidth limitations, determines the responsiveness and efficiency of your computer. Optimizing these elements is key to maximizing its potential for any given task. Test questions. 1. Explain the difference between RAM and storage devices, like HDDs or SSDs, in terms of data retention and typical usage. 2. What role does the motherboard play in a computer system? Be specific about its functions. 3. Describe the fetch decode execute cycle. Why is this process fundamental to how computers operate? 4. How does increasing the number of cores in a CPU affect performance? What types of tasks benefit most from multi-core processors? 5. What are the advantages of using an SSD over a traditional HDD? Explain at least 2 key differences. 6. Define bandwidth and explain how it impacts computer performance. Give examples of where bandwidth is important within a system. 7. Explain the function of the GPU and why a discrete GPU might be preferred over integrated graphics for certain applications. 8. Trace the path of data from when you double-click an application icon to when the application window appears on your screen, mentioning at least 4 key components involved.